Problem B6. Let A be the set of 2n positive integers 1, 2, 3 up to 2n, where n is greater than or equal to 1. For which values of n can this be split into n pairs of integers in such a way that every pair has a sum which is a multiple of 3? As always, in Olympiad problems such as this, you also need to explain why no other values of n are possible. However, we are not going to be doing the full explanation, so I'm just going to be showing how to get the answer. Consider these 3 cases. Case 1 is n is equal to a multiple of 3, and we're going to solve that case now. We list the set and that is the set. Now we are going to pair some of this, so I'm going to pair that, also that, and that's going to pair that, and so on and so forth. We get the sum of these pairings, 6k minus 3 for all of them, right? And now if 3k is a multiple of, if n is a multiple of 3, then 2n is also a multiple of 3. In this case, it's 6k, right? I think you get why it's 6k, it's just 2n. If you subtract 3 of a number that is a multiple of 3, you get a number that is a multiple of 3. So, we find that when all of these pairings converge into this value in the middle, the sum of this area of this set is going to be a multiple of 3. Now the point here is, if the sum of the whole set is a multiple of 3, then you can do all the pairings. Because, yeah, if you have multiples of 3 pairs, then the entire sum has to be a multiple of 3. The remaining 4 we can also pair up like this to get a sum of 12k minus 3, which is also a multiple of 3. Therefore, for n is a multiple of 3, you can do the pairing, and therefore is correct, is one of the options. We're going to put in the answer. Case 2. We're going to do it this way. Write the set, but then have 2n like that. Pairing, we get 2n plus 1. Now, if n is 1 more than a multiple of 3 and you multiply it by 2, it's going to be 2 more than a multiple of 3. And 2 more of a multiple of 3, you have 1 more, you get 3 more than a multiple of 3, which is a multiple of 3 itself. So this is a multiple of 3 in this situation above here. So therefore, all the pairings will also be a multiple of 3. And in general, we have the sum of the whole set to be a multiple of 3. So we have a big tick here. Now for this last set, I'm going to write 1, 2, 3, until 2n minus 1, until 2n. Now, we know that this pairing is 2n plus 1. And this pairing is also 2n plus 1. And so on. Now, we can notice something. The sum of the entire set is just n multiplied by 2n plus 1. Now, why is this? I'll give you a bit of thinking time. Okay. N is the number of pairs. I mean, it literally says in the question. It's literally just half of 2n. There are even number of positive integers in the set. So after doing this, we get the sum of the set. Now we know n is 1 less than a multiple of 3, right? So when you multiply it by 2, it's going to be 2 less, right? It's going to be 2 less. But then you add 1, which means it's going to be now 1 dash. And since it's 1 less than the multiple of 3, so 1 less than 3k, I'm just going to say that. And n is also, or n is just 1 less than 3k divided by 1, or divided by 2. So n is also not a multiple of 3, as we've seen before. So therefore, the whole multiplied product cannot be a multiple of 3. Therefore, the sum of the entire set cannot be a multiple of 3. Therefore, it is not possible. This case is not possible. So therefore, the answer to this question is all values of n that are either a multiple of 3 or one more than a multiple of 3. You of course don't have to write it this way, I'm just showing you, okay? So that is the answer to the question.